Hello, good morning. Myself, Dr. Shaila Dinkarapte. We'll continue with the lecture series in digital signal processing. We have already completed the discussion of discrete Fourier transform. Now we'll see how this discrete Fourier transform can be efficiently computed using the algorithm which is called as fast Fourier transform. So FFT is not a different transform, it is the fast algorithm for the computation of DFT. First, consider the formula for DFT. X of k is summation n varying from capital N minus 1 xn e raised to minus j 2 pi k n upon capital N. Similarly, I can compute xn as 1 upon n summation n k varying from 0 to n minus 1 x of k e raised to j 2 pi k n upon capital N. So, accept this sign for the e raised to factor and this particular dividing factor of capital N, the formulae are on similar lines. So, whatever computation or the efficient computation that we are generating for DFT is also valid for inverse DFT. Here there is a twiddle factor involved. So this e raised to minus j 2 pi by capital N, this particular term is called as W. And the base of this is capital N. And if you have to write k into n factor, we'll write it as write it at the top of W. So we'll write it as the superscript. So Wn is a twiddle factor e raised to minus j 2 pi by capital N. Why it is called as twiddle factor? Because it slowly rotates, and we'll see that there are properties of the twiddle factor, namely the periodicity and symmetry property, which helps us to compute the algorithm in efficient manner. So consider the properties of W. It is periodicity in the sense, suppose you consider 8-point DFT computation, W8 raised to 1 is same as W8 raised to 9, W8 raised to 17. So this is 0 plus 1, 8 plus 1, uh, 16 plus 1. So it repeats. This is called as periodicity. The period is capital N, and that is equal to 8 here. Similarly, there is a property called a symmetry property in the sense W8 raised to 1 is same as W8 raised to 5 with a negative sign. So this is symmetry property. This is same as this one with my same magnitude, but the sign is different. Similarly, all these factors, this one is symmetrical with respect to this point is symmetrical with respect to this point is symmetrical with respect to this point, and so on, right? Now let us see how the efficient computation of DFT will be carried out. What we'll do is we'll make use of the properties of the twiddle factor, and then what we do is we use divide and conquer approach. So if n is quite large, say n is equal to 2048, then in that case the computation becomes complex. So many complex multiplications and so many complex additions are to be carried out, so it becomes too complex. So what we do, we divide it. So each capital N point DFT computation is divided into 2n by 2 point DFT computation. So if it is n point DFT computation that we are supposed to carry out, we will divide it into two 4-point DFT computations. Again, these two 4-point DFT computations will be further divided into two 2-point DFT computations, that is n by 8-point DFT computations, n by 4-point DFT computations, and then n by 8-point DFT computations. We'll continue with this until we are left with only 2-point DFT computation. This is called a divide and conquer approach. There are two methods those are used under this divide and conquer approach. One is called as decimation in time, and second one is decimation in frequency. So let us see how these algorithms are designed. We also make use of butterfly computation for the 2-point DFT computations, because for 2-point DFT computations what we have to do is we have to just add the two components and we have to subtract the two components. Because of the nature of this particular graph, it is called as butterfly computation. A trick to solve 8-point FFT problem. So many times you will be asked to solve the 8-point DFT problem. So I am specifically giving you the hints. You will have to remember these points. W2 raised to 0 is 1. So anything raised to 0 is 1. W4 raised to 0 is 1. W8 raised to 0 is also 1. Then W4 raised to 1 is equal to minus j. W8 raised to 1 is 1 upon root 2 minus j 1 upon root 2. W8 raised to 2 is minus j. So this is same as W4 raised to 1. And W8 raised to 3 is 1 upon root 2 plus j 1 upon root 2. How to calculate this? This W is e raised to minus j 2 pi by capital N. So 2 pi by capital N here is 4, and because we have to compute 4-point DFT, we will have to write it as e raised to minus j 2 pi n is 1 by 4. That 2 will cancel with this 4, so it is e raised to minus j pi by 2. E raised to minus j pi by 2 is cos pi by 2 minus j sin pi by 2. So if I substitute, I get it as minus j. Right. So this is how we are supposed to compute it. This is cos of pi by 2, sin of pi by 2. We have to substitute and get the answer. So this is how we have to do it for W8 raised to 1, W8 raised to 2 and W8 raised to 3 as well. But if you just remember these points, the computations will be further very easy for you. Now let us see decimation and frequency algorithm. Here we divide the input n point sequence into two parts. So firstly, whatever 8 points we are getting, we just divide it into two parts. We'll consider first 4 points on one side, next 4 points on the other side, and then form n by 2 sequences Hn and Jn as using this formula. So Hn is computed as xn plus x of n plus capital N by 2, and Gn is calculated as xn minus x of n plus n by 2, and it is multiplied by, this whole bracket is multiplied by Wn raised to n. Compute n by 2 point DFT for Hn and Gn by repeating step 2 until we are left with 2 point DFT. So this is how we divide the n point DFT computation into n by 2 point DFT computations, and then further go on dividing until we are left with 2 point DFT computation. And finally execute the algorithm for 2 point DFT computations, and then what you will have to do is execute bit reversal on the output of DFT coefficients. Why this is required, we will just see. So let us consider the problem of 8 points sequence 1 2 2 1 1 2 1 1. This is suppose the sequence given to you, and you are supposed to find out 8 point DFT. Now step 1, what we do is divide the sequence into two parts. So we will just divide it into two parts. So 1 2 2 1 will be on one side, 1 2 1 1 will be on the other side. So this is how we just divide. We take the first 4 samples on one side, next 4 samples on the other side. Then step number 2, calculate Hn and Gn. So what is Hn? X of 0. H of 0 will be equal to x of 0 plus x of 4. X1 plus x1 is H1 is calculated as x1 plus x5. H2 is calculated as x2 plus x6. H3 will be calculated as x3 plus x7. So this plus this plus this plus this plus this. So it comes to 1, 4, 3 and 2. Is that right? Now compute Gn. So G0 is equal to x0 minus x of 4 into W8 raised to 0. W8 raised to 0 is 1, as we can remember. And x0 minus x4. This is x0, this is x4, so it is 0. So answer is 0. G1. G1 is x1 minus x of 5. So 2 minus 2 into whatever, it will be 0. Then 2 minus 1 into W8 raised to 2 means it is W4 raised to 1, so it is minus j. Alright. And x of 3 again is 1 minus 1 into whatever, it will give you a value of 0. So we have calculated Hn and Gn using the formula that we have already given. So what we are doing now, we are having this sequence 1 2 2 1, that is on one side, 1 2 1 1 on the other side. These are the 8 points those were given to us. We have divided it into two parts, and now what we do, x0 plus x4, x2 plus x5, x2 plus x6, x3 plus h7. So we get this hn, and we also calculate gn as we have just seen, x1, x0 minus x4 into w4 raised to 1 and so on. So we get the gn values, we get these hn values. Now using these hn values and gn values, what we have to do, we have to compute 4-point DFT. And using these values also, we have to find 4-point DFT. That will be called as iteration number 2. So in first iteration, what we have done, we have divided this 8-point DFT computation into two 4-point DFT computations by calculating this HN and GN. Now we'll go to iteration number 2. So after iteration 1, note that the output DFT coefficients are decimated, that is divided in two groups, one consisting of even number samples and the other consisting of odd number samples. In iteration 1, we have divided n-point DFT computation problem into two 4-point DFT computations. So in this case, n by 2 is equal to 4. So we have divided 8-point DFT computation into two 4-point DFT computations. Therefore, we have to continue with step 1 again for HN and GN, that we have already given the formula, and we will divide each 4-point DFT computation into two 2-point DFT computations. Right. So let us see how iteration 2 would look like. So we'll have to calculate h dash 0 and h dash 1. So we'll consider h0 plus h2, then h1 plus h3 on similar lines. Then g dash 0 is h0 minus h2 w4 raised to 0, h1 minus h3 w4 raised to 1. Similarly, we'll calculate h double dash 0, h double dash 1 using g0 and g0, g1, g2 and g3, and then calculate g double dash also on some lines. This is iteration number 2. So what has happened? This 8-point DFT, 8-point signals we have considered. We have divided it into two parts. We have calculated this HN and GN. Now again we do the same thing. 2 plus 3, 5. 4 plus 2, it is 6. Then 2 minus 3, it is equal to minus 1 into W raised to 0, W4 raised to 0, that is 1. Then 4 minus 2, that is 2 into minus j, so minus 2j. So similarly, we compute the values over here also. Now we have to carry out 2-point DFT on these values. So we have divided 4-point DFT problem into two 2-point DFT problems. And finally, what has happened is the DFT coefficients that we get are in this order: x0, then we have x4, x2, x6, x1, x5, x3 and x7. Now we'll write this 4 as 001, 2 as 010, 6 as 011 and so on. So we write it in the binary form, and let's see how what happens here. So in the iteration number 3, what we have to do is we have to compute this 2-point DFT computation. 2-point DFT is just the butterfly computation. So 5 plus 6 and then 5 minus 6. This is minus 1 plus minus 2j and minus 1 minus 2j. Right. So you just have to add and subtract and you get these values. But what is the order of these DFT coefficients? This is x0, this is x4, this is x2, this is x6. So just let us write it in the decimal format, in the binary format and see. See, the DFT coefficients order is x0, x4, x2, x6, x1, x5, x3 and x7. Now let us write for the 0, I will write 0, 0, 0, x4 I will write 1, 0, 0, x2 I will write 0, 1, 0, x6 is 1, 1, 0, x5 is 0, 0, 1, x3 is 1, 0, 1 and x3 is 0, 1, 1 and x7 is 1, 1, 1. So now we have to do the bit reversal, because 1, 0, 0, if we do the bit reversed, you will get 0, 0, 1. So it will be the first coefficient, right? So you will have to carry out the bit reversal on the output sequence. That is the last step in the computation. So what we do is the final step in the algorithm is a bit reversal process, right? So after bit reversal, we'll get the correct order. So let us see. This is x001. So where is x001? This is here. That is the 1, 2, 3, 4, fifth value. 1, 2, 3, 4, fifth value. This fifth value should be replaced here, 0 minus 0. So similarly, if we replace the other coefficients also, we will get the correct order of the DFT coefficients, right? This is called as decimation in frequency algorithm, because in the output we get the output as the decimated output. Okay. Another algorithm is also there which works as decimation in time algorithm. Now let us see what is in place computation. In place computation deals with the number of memory values those are required for computation. So let us consider this Hn and Gn. See, once we have calculated Hn and Gn using xn and x of n plus n by 2, this xn and x of n plus n by 2 is no longer required further. So the memory location which is used to store h1, hn and h of n plus n by 2 can be used for storing the values of hn and gn. That is what is called as in place computation. Let us see how the computational complexity can be calculated. Now consider DFT for 8-point computations. So 8-point DFT computations, we require roughly n into capital N computations. So 64 computations. But if you consider DFT, if we consider the computation of FFT, it will require n log to the base, log n to the base 2. That is n means 8, 8 multiplied by log 8 to the base 2, that is 3. So 8 into 3, 24. So 24 computations as against 64 computations. But if n is very, very large, then there is a significant saving, significant reduction in the number of computations. So uh, this is the efficient algorithm because the number of computations required are reduced. Why this is so? Because we are dividing the 8-point problem into 4-point problem. For that we have to just compute two complex multiplications and two complex additions. And for the 4 to 2 again, there is only one complex computation that is required. So the number of computations required finally comes to n log n to the base 2. This the reader can verify that it comes to log n to the base 2 into n, that is 24 computations. Then we go to the next algorithm, decimation in time algorithm. In this case, you can remember that the process is completely reversed. So in the earlier algorithm called as decimation in frequency algorithm, we have calculated or we have executed the bit reversal at the end. Now in this algorithm, we will do the bit reversal as the first step. So bit reverse the input sequence, then divide n point DFT into n by 2 point DFT, same as before. So we calculate HK. HK is we calculate xk, it is hk plus wn raised to k gk. But what is hk? Hk is summation x of 2n w raised to nk to the base n by 2. Similarly, this is gk calculated using x of n plus 2, that is odd number of values. This is using even number of values. And if n by 2 is not equal to 2, again repeat step 2, else compute 2-point DFT computation. So same as before. So just see. Iteration number 1. Let us take the values 1, 2, 2, 1, 1, 2, 2, 1, same as before. Now what we have to do? We have to decimate first. That means divide the sequence into two parts. But how to divide it into two parts? Consider even numbered coefficients and odd numbered coefficients. So even numbered coefficients, we will consider 1, 2, 1, 2, and then decimate again 2, 1, 2, 1. This will be the other sequence. Okay. Now, use this sequence x0, x2, x4, x6, x1, x3, x5, x7. So even numbered coefficients, odd numbered coefficients. Execute 4-point DFT. Here also execute 4-point DFT and compute HK and GK. Now after you compute this, you just have to calculate again x0 is same as h0 plus g0, h1 plus g1 and so on. So if you look at this particular flow graph, you will find that it is exactly the reverse. Just see how we calculate it. So we start with 2-point DFT now. These are the 0, x0, x4. Firstly, we had x0, x2, x4. So we, in order to divide it, what we do, we just again divide the sequence into two parts with even numbered and odd numbered. Now x0, x2, x4 and x6. Out of this, if we consider even values, we will get x0 and x4 on one side, then x2 and x6 as the odd number, and then compute 2-point DFT. So this becomes now complete bit reversal. And then after 2-point DFT computation, you compute 4-point DFT computation, and then you compute 8-point DFT computation on these computed values. Okay. So start with 2-point DFT with bit reverse input. So these are the values x0, x4, x2, x6, x1, x5, x3 and x7. Now what you do, you just add and subtract and can execute this 2-point DFT computation. Now on this two 8-point DFT computations, we consider 4-point DFT computation on these on these 4 points. So how to calculate? 2 plus 3, it is 5. 0 plus 0 plus 1. So this is 0, this is 1, this is minus j. 2 minus 3, it is minus 1. 0 into minus 1 into minus j. So it becomes plus j. So W4 raised to 1. The j minus j is W4 raised to 1. Similarly here, 4 plus 2, 6. 0 plus 0 is 0. Then 4 minus 2, that is 2 into W4 raised to 0 is 1. Then 0 minus 0, so it is 0. So it's not getting j anywhere in this case. Now again here, 4, this is 5 plus 6, it becomes 11. This is minus j plus 0, it is 0 minus j. Minus 1 minus 2j. This is j minus 0, so it becomes j. Then this is 5 minus 6 is minus 1, minus j into minus 0, so minus j, minus 1 into 2 plus 2 into W8 raised to 0, sorry, W8 raised to 1, so it is j. Here also you are getting j. So you just first start with the bit reverse sequence, then compute 2-point DFT computation, then calculate this 4-point DFT computations, and then calculate 8-point DFT computations. Now, but how you go about doing it? You will have to use that HN and GN formula. So decimation in frequency is exactly, the flow graph is exactly opposite to that of decimation in time. So we can note that for decimation in time algorithm, we start with the bit reverse sequence, and the last step in the decimation of frequency FFT is the first step in the decimation in time FFT. If we compare the flow graphs for iteration 3 for the two algorithms, we see that they are exact mirror images of each other. We can say that the algorithm of decimation in frequency FFT is a dual of decimation in time FFT. Because of this exact reverse mirror image nature, it is called as the dual. So these two algorithms are dual of